So here's our last linear programming problem. And what I want to do for this one is, rather than making the table like we have earlier, I want to skip straight to trying to write the initial linear program just from the prompt. So let's try to talk through that. However, I think this might be a good one for you to try on your own if you want some additional practice for setting up word problems. So if you'd like, you can pause the video and try setting up the initial linear program before I do. And if you want an extra challenge, you can try solving this whole problem on your own before I do. But let's get started on it. So here, a farmer has 110 acres available, and he wants to plant some sort of a mixture of potatoes, corn, and cabbage. Costs him $400 to produce an acre of potatoes, $160 to produce an acre of corn, and $280 to produce an acre of cabbage. He has a maximum of 20 grand to spend, and then we also know his profits for each of those crops. And the question is, how many acres of each kind of crop should he plant to maximize his profit? And then afterward, we're asked how much land will remain unplanted, and to explain this. So we will fully solve this problem because I think it's a good sort of compact example. So let's decide what it is that we're trying to maximize and what it is that our variables should represent. So because we're looking for how many acres of each crop we want to plant, that would be a good thing for our variables to represent. So I'm going to let x1 be the number of acres of potatoes, and then x2 will be the acres of corn, and then x3 will be the acres of cabbage. So those are our variables. Now what we want to do first is we want to decide our objective function. So I'm going to call it P for profit. We're trying to maximize profit. We know that we make $120 per acre of potatoes, $40 per acre of corn, and $60 per acre of cabbage. So if I wanted an expression for the total profits, it would be $120 per acre of potatoes times the number of acres of potatoes, plus $40 per acre of corn times the number of acres of corn, plus $60 per acre of cabbage times the number of acres of cabbage. So there's our expression for the total profit. And now we have some constraints. So we will have two constraints that I'm going to use. So first of all, we have an acreage constraint. So we have a total number of acres. And we also have a budget constraint. So let's write down those two constraints. And if it helps you, you can write down the right side first. I normally don't, but it might help you. So we know that the total number of acres would need to be less than or equal to 110. And also the total budget is going to be less than or equal to 20 grand. So if you have trouble deciding what things should represent the objective function and what things should be represented in the constraints, it helps me to try finding phrases like a maximum of or some number of acres available. Those tend to be constraints. And then the thing that will end up being the objective function is just going to be whatever it is that we're told to maximize. So here we're trying to maximize profit, so we know that that expression for profit is just going to become our objective function. And then because we have only a certain number of acres available and only a certain amount of money available, those two things, the acreage and the budget, should end up being these constraint lines instead. So on the left side here, I need to express the total number of acres that we use. But remember that x1 is the number of acres of potatoes, x2 is the acres of corn, and x3 is cabbage. So if I wanted the total acreage that we're going to be using, it would just be x1 plus x2 plus x3. So that gives me the total number of acres that we're going to use. The budget constraint is a little bit different. So here we know that it costs $400 per acre of potatoes. So the total amount that we're going to spend on potatoes is 400 x1. And then it costs 160 per acre of corn, so that would be 160x2 as my cost from corn, and then 280 per acre of cabbage times the number of acres of cabbage that we make. So that will give me my total budget. Okay, so this is the initial linear program with this implicit assumption of non-negativity for all three of these variables. So here's our initial linear program. Now we're going to translate, Now we're going to translate this into a corresponding initial simplex tableau. So maybe I should scroll a little bit. There we go. Okay, so for our initial simplex tableau, I normally like to label the columns. You don't have to label the columns if you're already comfortable just writing down what the simplex tableau should be. Notice that here there are two slack variables. That's because there are two non-trivial constraints. So each new constraint needs its own slack variable. If I translate the first constraint, then it would be a 1, 1, 1, 1, 0, and then 1, 10. Remember this right side column, I'm labeling it as P because P is going to be this bottom right value, but it's technically recording the coefficients, or sorry, the constants on the right sides of these equal signs or inequalities. So this is what I get for the first one. Notice that I needed to use my first slack variable for the first constraint. Similarly, for the second constraint, I would get a 400, 160, 280, and then a 0, 1, 20 grand. We had to use our second slack variable for the second constraint. And then if I rearrange the objective function so that all of the variables appear on the left side, then the coefficients would be negative 120, negative 40, negative 60, 0, 0. And remember that here this is the right side of the resulting equation. It's not the coefficient on P anymore because we deleted the ordinary P column. So this would just be a 0. And it will always be a 0 to start with. So that's what we have as our initial, that's what we have as our initial simplex tableau. So now we need to optimize. So we want to find the maximum value of P that we can get subject to all of these constraints. So we'll use the simplex method here. First, we look for the most negative indicator, that's this one, so that will be our pivot column. And then we compute those quotients. Remember, the quotient is the far right number divided by the positive numbers in this column. So the quotients here would be a 110 divided by 1, which would just give us 110. And then a 20 grand divided by 400 would give us 50. Now 50 is smaller than 110, so we pick the smaller number here, and that tells us which row the pivot lives in. So this is our pivot row, and this is our pivot column, so that means that this is our pivot 400. And remember, our first step is to take the pivot and turn it into a 1, so I would take the pivot row and divide by the pivot. So we're taking row 2 and dividing by 400. Now if we do that, then the resulting matrix is going to be this. So we'll still keep the same top row. If we divide the middle row by 400, we should get a 1, and then for this one I am going to reduce the fractions just to make it a little easier to read. But ordinarily, if I were doing this with just scratch work, I would not be reducing any of these fractions. And then for this last entry, it would be 20 grand divided by 400, but that's the quotient that we computed a second ago. We know that that quotient is 50. So we'll have that. And then our bottom row, again, is also not changing, so we'll have our original bottom row. So this is where we're at so far. And now I'm going to decide on this page what the next row operations should be, and then I'll just show you what the resulting matrix is on the next page. So we have our pivot as a 1, and now we need to use that pivot to eliminate the rest of the entries in that column. So if I wanted to eliminate that first entry in row 1, I would take row 1 and subtract what's beneath it. So we'll have row 1 minus the pivot row. And then to fix the bottom row, I would take the bottom row and add 120 times the pivot row. So those are the row operations we want. And if you'd like, you can pause the video and do these row operations on your own to just confirm that you're doing everything correctly. This will require you to work with some fractions, or again, if you'd like, you can, instead of putting 2/5, you could put a 0.4. You can do everything with decimals. That's totally fine. But what I get as the resulting matrix is this. The top row should be a 0, 3/5, 3/10, 1, -1/400, 0, 60. The middle row is not changing from what we had previously. So the middle row will still be this. And then the new bottom row is going to be a 0, 8, 24, 0, 3/10, 1, 6,000. So we would continue repeating this procedure until we had eliminated all of the negative indicators, but thankfully that's already happened. So even though we started with 3 negative indicators, our first step managed to get rid of all of them. So now we don't have to do any further pivoting. We don't have any negative indicators remaining, so now we just need to read off the solution because we know that this simplex tableau corresponds to the optimal solution. So I'll relabel the columns. Oh, I'm sorry. I forgot that we were suppressing this row, or this column. So I didn't suppress it in my original notes, so you might see that column in the other notes. But here I was just labeling this last column as P for profit. So this is the simplex tableau that we should end up with. And now we can read off our answer. So maybe let's first scroll up and see what it is that we actually needed to answer for parts A and B. So in part A, it just says how many acres of each crop should we plant. And then in part B, it says if we maximize profit, how much land would remain unplanted. So remember that the amount of land that would remain unplanted, that would be the amount of slack that we have in this first constraint. So if we had any slack in this inequality, then that would be the amount of unplanted land because the rest is the amount of planted land. So in other words, S1 is going to correspond to the amount of unplanted land because it is the slack from that first inequality. So we're also looking at the value of S1 for the amount of land that goes unplanted, and then we need to explain that value. Okay, so let's scroll back down here so that we can read the answer. So if we want to read the solution here, then that means we should be eliminating, we should be eliminating the non-basic columns. So I'll eliminate those 3 non-basic columns. Remember, we never eliminate that last column. We're just going to use it to read off our value of P. So what we get is that x2 and x3 are equal to 0. So is s2. And these others we'll need to read off by translating the corresponding rows into equations. So I would get an x1 value of 50 and an s1 value of 60. And from these we can answer our questions. So we would plant 50 acres of potatoes, and that's it. In other words, no other crops should be planted because x2 and x3 were 0. In part B, the question was how many acres will go unplanted. So here, notice there were 2 slack variables that we had to worry about. S1 was the number of acres that we would have left over, and S2 was the amount of budget that we would have left over. So notice that we'll have 60 unplanted acres. But because the profits on potatoes were so much better than the other crops, it's actually worth it for us to blow our whole budget on potatoes. So we spend all of the money that we have on potatoes and leave 60 acres unplanted. And the benefit of doing that is just that we're spending all of the money that we possibly could on potatoes, which give us the best possible profit. So I would say that we have 60 unplanted acres, but spending on potatoes is worth it. So we have blown our whole budget, which is why we have so many unplanted acres. And it might seem like this is an inefficiency because we have so many unplanted acres, but it is worth it in terms of driving the profit to just spend all of your money on this most profitable crop. So this is the best that we can do here. All right, so this is the end of section 7.5. Section 7.5 is just sort of the word problem versions of section 7.4, where we introduced the simplex method. Next week, we'll talk about a slight complication, which is what you can do to solve similar problems whenever the initial linear program is not standard. So we'll start to see some variations of linear programming problems that we're still able to attack, but that aren't quite as nice as the ones that we've been using so